Hi, this is my video number 11. Right. In the previous video number 10, I've given example on how to determine the iterated kernel for the non-homogeneous Freedom integral equation, as well as how to determine the resolvent kernel for the Freedom integral equation. Alright, in this example, I'll explain using the iterated kernel or resolvent kernel, we are going to solve the non-homogeneous Freedom integral equation. Alright, so let me recall that the Freedom integral equation, a non-homogeneous Freedom integral equation, we have ux is equal to fx plus lambda a to b kxt ut dt. This is a non-homogeneous Freedom integral equation, and the resolvent kernel, the resolvent kernel is can be written as r xt lambda as a summation of m from 1 to infinity. We have lambda m minus 1 k mxt. That's for the resolvent kernel. And the solution of the non-homogeneous Freedom integral equation can be written as, once we can find the resolvent kernel, then the solution is given as, solution can be written as ux is equal to fx plus lambda a to b r xt lambda ft dt, where the km as the iterated kernel, we have where we can write k1xt as kxt, and km xt we define as integrate a to b kxs km minus 1 st ds. So in order to solve Freedom integral equation, nonlinear non-homogeneous Freedom integral equation using the iterated kernel and the resolvent kernel, so we need the iterated kernel as well as we need the resolvent kernel. So let's see example. Okay, we solve the, let's say, given the Freedom integral equation, non-homogeneous Freedom integral equation, plus half integrate 0 to 1 xt ut dt. Okay, so if you compare that with the non-homogeneous Freedom integral equation, what we can see that our fx is 5 over 6x. So that's your fx is 5 over 6x. Your lambda is half, and k kernel is xt. Kxt is xt, and a 1 and b a is 0 and b is 1. So a is 0, b is 1. Then using the iterated kernel, we can find, using the iterated kernel, we can find k1 xt, which is by definition is k xt, and our kxt is xt, and we can find k2 using that Okay, we can find k2 xt. This is integrate 0 to 1 k xs, so we have xs, all right, and then k1 st, so k1 st is kst, so kst, this is st ds. Okay, I think this is not difficult to evaluate. So we have you can take out xt 0 to 1, we have s squared ds, that give you s cubed over 3, so you have 1 over 3 xt, right? And then we can find x3. You can find x3. This is integrate 0 to 1. We have k xs k2 x st, k2 st ds. So we have this is 0 to 1, kxs is xt, xs, k2 given as that, so we have 1 over 3 st, so st ds. So that we have 1 over 3 integrate xs, integrate 0 to 1 xs st ds. So this is just the same as the previous case, so that will give you 1 over 3 squared xt. Okay, so from here we can have basically up to m iteration. So we can, if we can proceed this, we have the general form already. So we have km xt is given as, so we have 1 over 3 there, to the power for 3 power 2, for 2 power 1, so m means power m minus 1 xt. So we have xm, right? And then you can write from there, we can write the resolvent kernel, which is defined here. Okay, so using this definition of resolvent kernel, we have R. So therefore R xt lambda, right? This is, we have summation m equal to 1 to infinity, we have lambda m minus 1 km xt. Okay, so you can write this sum equal to 1, m equal to 1 to infinity, our lambda is half m minus 1 km is we obtain here, this is our km, so we have 1 over 3 m minus 1 xt, right? Okay, so of course you can simplify that. So this is, you can write this m 1 to infinity, this is 1 over 6 m minus 1 xt. Alright, this is the geometric series. We have a r n. This summation is a over 1 over r. Okay, so using that, so our a is 1 here, so we have 1 over 1 minus our r is 1 over 6 xt, that give you 5 over 6, so 6 over 5, right? 6 over 5, yeah, 6 over 5 xt. So therefore we can find the solution. Ux is given as fx plus lambda integrate 0 to 1 rxt lambda ft dt. Okay, so this we have our fx is 5/6 x plus lambda is half integrate 0 to 1, our r is 6/5 xt, and our ft is 5/6 t. Yeah, from ft is we take ft from fx. You just change t with x. So here we have let me put this in bracket. So we have 5/6 t dt. So this is easy to evaluate, right? So we have this is 5/6 x plus half. You can take out x integrate 0 to 1, so we have t squared dt. That give you 5/6 x plus this is 1/3, so 1/6 x, that give you x. Okay, so therefore the solution is given as ux equal to x. Of course, you can we can check our solution here. If we substitute into the equation ux equal to x, you can just substitute there. You substitute that with t, then you can find left hand side equal to right hand side. That to verify that our solution is correct. All right. So in the notes, I've given the example, well, without the solution, of course. I just wrote down the solution. So I hope you can do that as an exercise. Okay, let me give another example using the what we call successive approximation. Yeah, successive approximation, where we cannot have the resolvent kernel cannot be written in the closed form. Yeah. So in that case, yeah, the resolvent kernel cannot be written in closed form. Yeah. So in that case, we use the successive approximation. Successive approximation, where for the successive approximation, we can find u and x, where u and x is given as fx plus lambda integrate a to b kxt un minus 1 t dt. So normally we compute up to third order. Yeah. And normally u naught is given as u naught x is given f. We can take as a fx. Yeah. If it's given beforehand in the problem, then we have to use the given u naught. Else we can take u naught as fx. Okay, so let's say example. Solve the let's say we have ux equal to 2x plus lambda 0 to 1 x plus t ut dt. I think you can also solve using a degenerate kernel or separable kernel. But now you want to use the successive approximation. Use successive approximation. Now, for the successive approximation, excuse me, we use that approximation. We can find u1 given u0. So in this case, here u0 x is given as 1. Okay, and our kt is x plus t. So therefore we can find un x. This is fx. Our fx is 2x here, 2x plus lambda 0 to 1. Our kxt is xt, and un minus 1, sorry, this is x plus t. So un minus 1 is, put it un minus 1 t dt. Now we have u0, so you can find u1. From there you can find u1. X is 2x plus lambda 0 to 1 x plus t u0 t dt. Okay, so from there you can find 2x plus lambda 0 to 1 x plus t. u0 is 1, so we have 1 dt. So it is not difficult for you, of course. This is 2x plus, we have lambda, we have xt, so you got x there, plus this one t squared over 2, so we have 1 over 2. Okay, so that's the first approximation. You can find the second approximation, u2x. This is 2x plus lambda 0 to 1 our kxt, which is x plus t, and then un minus 1 is u1 t dt. So you can substitute into that. This gives you 2x plus lambda 0 to 1 x plus t. Our u1 is t, so we have 2t plus lambda t plus half dt. Alright, so you can you can rewrite those things. 2x plus, we have lambda, you can take out x, then 0 to 1, so we have 2t plus lambda t plus half, that's one terms, dt, plus lambda t, integrate 0 to 1, we have t, 2t plus lambda t plus half dt. Okay, so from there we have this is 2x plus lambda x, integrate 0 to 1, we have 2 plus lambda t plus half lambda dt, plus that one, lambda integrate 0 to 1, so here we have t squared, so 2 plus lambda t squared, and plus half lambda t. dt. Then of course this is not a big deal for you to solve that one. That give you 2x plus we have lambda x, and then we have that one t squared over 2 evaluate 0 to 1, so we have 2 plus lambda over 2, correct? This one 2 plus t squared over 2, so right. And that one you have plus, so we have this thing, and plus lambda t, so we have half lambda, correct? And then for that one we have lambda integrate z with respect to t, so t cubed, so we have 2 plus lambda 1 over 3 plus this one is t squared, so 1 over 4 lambda. Right, because t is 0 to 1, so yeah. Okay. So then you can simplify this. This will give you 2x plus, you arrange that in terms of lambda, so we have a lambda, then we have one x here. Alright, so we have x plus, here we have half lambda, so you got lambda, right? X, and then we have another lambda here 2 over 3 lambda here, okay, plus 2 over 3, so you got 2 over 3 lambda. So we've done that, we have done that one. Then for lambda squared plus, here you have lambda squared x, okay, so you have lambda squared, you can arrange that. Here you have another lambda squared, half, you got 1, so we have just x here. And for this part, just lambda squared, we have that and that, so we have plus I think 1 over 3 plus 1 over 4 for lambda squared, yeah. Okay, so this you give you 2x lambda x plus 2 over 3 plus lambda squared. This one give x plus 12 7 over 12. That is second order. Then you can find third order u3x. This is 2x plus lambda integrate 0 to 1. Our xs is x plus t u2t dt. Keep on doing this. So this is 2x plus lambda 0 to 1. So we have x plus t here, x plus t, and then u2t is given here, so you can just put everything there. 2t plus lambda t plus 2 over 3 plus lambda squared t plus 7 over 12 dt. Alright, again that's straightforward. I don't want to do that. I just give you the solution. This give you 2x plus, and remember to arrange according to lambda. So we have lambda x plus 2 over 3 plus lambda squared 7 over 6 x plus 2 over 3 and plus lambda cube 13 over 12 x plus 5 over h. Of course, you can find x4, you can find x5, and so on, but for the successive approximation, up to order 3 is enough. Okay, so with those two examples, how to use successive approximation, we use the iterated kernel, we use the resolvent kernel, and with those examples. Okay, now let me talk on the reciprocal function. Reciprocal function. Okay, so what is the reciprocal function? Yeah, so if you let the kernel k xt, this is kernel to of a Freedom integral equation. So let's say this k is real and continuous on some rectangle I R given as x b and t a b. Okay, so this is your R. So basically your R is all x t such that x in AB and T in AB. Of course, I can write those things like that. Okay. Then there exists KRXT, yeah, provided that M B minus A less than 1, where M is maximum of this value KXT less than equal to M. Okay, so this KR satisfy, so KR, so we have KR, you can write this K RT XT plus K XT equal to integrate A to B K R XS K ST DS. So this KRT we call it as a reciprocal kernel. KR XT, we say this is a reciprocal kernel to K and vice versa. Yeah, reciprocal kernel to K XT. Okay, so let's see how can we get those so by definition of the iterated kernel, we have by definition of iterated kernel, with the iterated kernel, we have K1 xt, this is K xt, and Kn xt is equal to integrate A to B Kxs Kn minus 1 st ds. Now we write minus K R xt as K1 xt plus K2 xt plus Kn xt plus and so on. So you write that way, where k is the real and where kr is real and continuous. So this k real and continuous on R. Okay, then we can write this, and of course here in this case we need this series, we need that series uniformly, absolutely and uniformly convergence for m b minus a. So we need this series absolutely and uniformly convergence, absolutely and uniformly convergent. Convergence for m b minus a less than 1. So I can write those series. I can write those series as we can take out k1 to the left and leave the rest to the right. So we have minus kr xt minus k1 xt. This is equal to k2 xt plus so on, kn xt and so on. Okay. And k1 is equal to k, so I can write this as a minus k r xt minus k xt. This is on the left side. On the right side we have k2. We can use the iterated kernel, definition of the iterated kernel here. So we have for k2 we have a to b, there's a k is k1, yeah, k is k1, so I can write this as k1 xt, and then k2, so we have k1 st ds, and I can write for k2, I can write for k3 and so on. A to b k1 xt, this is xs, yeah, s. So xs k2 st dt and so on up to n. So we have integrate a to b k1 xs kn minus 1 st dt ds and so on. All right then. So of course from there you can rearrange those. Yeah. Now k1 st. Now I can write this as a k2 k1. I can write this as a kn minus 1 k1. Yeah. So I can write this as a integrate a to b k1 xs k1 st dt plus integrate a to b k2 xs k1 st dt and so on. Integrate a to b kn minus 1 xs k1 st dt, right? And I can also have this, I can write those as a integrate a to b we have k1 xs plus k2 xs, we just factor out those things, plus and so on. We have k n minus 1 xs and so on. We just take out k1 st dt. From that we factor out k1, so we have all these things. And notice that this k1, k2 up to kn is equal to that k1, k2 up to kn. This is minus k r. So what we have now, so this is equal to, so we have with that, so we can write kr xt minus here minus k xt. This is, we have negative of a to b, all this is kr xs k st dt. So this minus, so we have plus everything. So we have that. Now again, this kr, as we mentioned here, this kr is a reciprocal kernel to k, and vice versa, k also reciprocal kernel to kr. K is real and continuous in R and satisfy that. Okay, and the reciprocal kernel is always exists. Reciprocal kernel to k is always exists. You can say kr xt always exists. Provided that the series, oh, I've written somewhere here. Okay, so kr xt is always exists, provided that those series here, that series, so let's call this star. So provided that star uniformly convergent, and of course it's converged because we have the condition n minus 1 m b minus a less than 1. This is given in our earlier statement. Okay, so with those basically explanation of the reciprocal kernel, so I think I stop here with this video. So let me conclude what I have done. Basically, I consider two examples on how to use the reiterated kernel and resolvent kernel to solve the non-homogeneous Freedom integral equation. Alright, so the first case where we can write the resolvent kernel in the closed form, whereas in the second example we cannot write the resolvent kernel in the closed form. In that case, we obtain the solution as the approximate solution up to order 3. Alright, so with that, I thank you. We can continue with the next video. Bye.